Okay, just thought I'd go through this question. A couple of people have been asking me questions about it, and this is probably one of the trickier ones. Unlike the other ones we did during our class the other day, this one doesn't explicitly give you values at certain times, so it's a little bit trickier. Anyway, let's um let's first just read through. An isotope of cesium has a half-life. Now, half-life, that seems important of 22 years. So initially we think, oh, years, that seems like time. So T is equal to 22. Half-life, what does that mean? Okay. Anyway, and its radioactive decay is proportional to how much cesium is left. So that's what this is saying here. So the rate of decay, so dN dt, is proportional to the amount that is left multiplied by some sort of constant R. Okay, cool. They've given you the equation, so that sentence is kind of irrelevant. But anyway, if they hadn't given us the equation, that sentence would be how we figure out what this equation is. Find how long it will take to reduce the cesium to 10% of its initial value. All right, so they don't tell us what the initial value is, but we're trying to figure out when it's 10% of its initial value. Okay, so at the moment, let's just sort of write down, we don't know the initial value n0, so we could say nt, right, at any time. N0, that's the initial value. We don't know that, okay, and we are trying to figure out the time when n is 10% of the initial value. Cool. And we know when t is equal to 22, so after 22 years, that's when it has a half-life. Right, I'll just write that there because it's always good to just, when you're not sure what to do, write down all the things you know and then start doing other things that you know, and hopefully you'll be able to figure out some things. So that being said, I've gone ahead and just done all of this working because this is the working that's the same every time. If you end up with this differential equation, the rate something changes is proportional to itself multiplied by some sort of constant. You know this is always going to work the same, okay? It's always going to be the same, but I'll just talk through it rather than writing it, so that we take the n to the other side, so it becomes 1 over n. We take the dt over to this side, no worries. Now when we integrate n, it becomes ln n, that's confusing. When we integrate minus r, because that's just a number, we integrate a number, it's just that number times by t plus c. Fantastic. Can we just delete all of that? Cool. And then to get rid of the ln, okay, you can see I'm not even writing this down because it's such a obvious thing that what I've done. It's kind of like not bothering to write that I'm dividing by 2 on both sides to get rid of something. I go I want that to be red. I go e to the power of ln n, because e to the power of ln basically cancels out, or cancels out the n, okay? And then we do that on both sides, so it's e to the power of that. So that's how I've gone from this line to this line. Cool, so that's got rid of the ln, so I've got n equals, now that's all to the power of e. And as we said the other day, e to the power of something plus something is the same as e to the power of that one thing multiplied by e to the power of that thing. If you've forgotten, right, x to the power of a times x to the power of b is equal to x to the power of a plus b, right? I've gone from here to here, yeah? Okay, and then we also know, right, when time is equal to 0, so 0 times minus r gives me 0. When time is equal to 0, the amount of cesium is the initial value. So we write down the initial value just as a variable because we don't know it. E to the power of 0 is 1. So 1 times e to the power of c equals the initial value. So that's why now we've replaced e to the power of c with that. So now we have an equation in terms of the initial value and in terms of this rate of decay. So we don't know any of that yet. Okay. Right, so continuing on. So now we know this. We figure we need to figure out the initial value, and we need to figure out this value t, because otherwise we're not going to be, otherwise we're not going to be able to figure out the what are we trying to find? How long it will take? Yeah, we're trying to find the time when n is 10% of NO. Okay, now normally we're given some value n at some value t, right? And we use that to find what r is and whatever. And normally we're given the initial value and stuff. We can see we don't have that. So we think, okay, so how are we going to be able to somehow set up equations using this to be able to figure out something? Right. So yeah, it's recording. Sorry, I've been editing a little bit. So the key is thinking about this half-life thing. Now, if this was an exam question, there'd be probably some more information that explain what half-life is. Half-life means after this amount of time, there's half of what you had. So in this case, after 22 years, if there was 8 kilograms, after 22 years, you would end up with half of that. So you'd end up with 4 kilograms, right? After another 22 years, you would end up with half of that, 2 kilograms, etc., etc. So, and I just realized that's out of the screen, but that's okay. You could listen to that. So what that means is if it has a 22-year half-life, that means we can write when t is equal to 22, the amount of cesium, which is n, is equal to half, or 50%. So how do we find half or 50%? We times it by half or times it by 0.5. So it's 0.5 of the initial amount. Remember, we don't know the initial amount. We don't know the initial amount, so we just write it like that. Okay, so we know when t is equal to 22, n is equal to 0.5 of the initial amount. So we think to ourselves, okay, how can this help us? Let's see. Let's write it down over here. T equals 22. N is equal to half or 50% or 0.5 of the initial amount. So now we can substitute in for T and we can substitute in for N. So let's go back to black. So now N is 0.5 of NO, of the initial amount. And is the initial amount there? We don't know that. And now we know it's 22, T equals 22. So 22 times minus R is minus 22R, right? So we've got that, okay? And now we could see if I got this NO and took it to this side, what are we going to do? We're going to end up with NO divided by NO, which of course equals 1. Now I'm not going to bother writing that. I'm just going to, I just know that what that means now is, oh, that's frustrating. Let's just keep that mistake in and we'll just rewrite it. It's no big deal. So what did we have again? We had 0.5 NO equals NO times that. So yeah, anyway, when we have two things that are the same on either side and they're multiplied, well, we know if we took one to the other side, they'd divide by each other, which cancels down to 1. So all I really need to do, because I'm in year 13 and I don't need to show all of those really simple steps, we just go like that. So now I'm left with e to the power of this equals 0.5. So now we can see I'm only left with r. So if I'm just left with r, that means I should be able to solve for r. Now if I'm trying to solve for r, then I may as well put that, oops, that's not what I want. I may as well put that on the left-hand side because that's where I'm used to putting things I want to solve. 0.5. And this is where I go, well, r is up in the power, right? And I think about, what do I do there? I've got an e here. I want to get rid of the e. So how do I get rid of the e? I put ln here, and I put ln here, right? ln on both sides. When I do ln of e, that essentially cancels out the e and leaves me with negative 22r. Got to do it on both sides, so we're left with ln 0.5. Now that's just a little bit more of an explanation where if you looked at my working, no, next slide. If you were looking at my working here, you can see I don't show that at all because I just know I'm putting an ln here and I'm putting an ln here. Okay, that's the kind of thing that we don't actually need to show. We don't actually need to show that we're doing that. It's kind of like we don't need to show that we're multiplying both sides by 2 or something like that. Anyway, are we still on black? Yes, we are. And so now, of course, we can solve because we've got ln of 0.5. Remember to use the ln button, not the log button, because this is log to base e, divided by negative 22. We can easily do that on a calculator. So I get r is 0.0315. And so now I substitute r back into the equation here, and now I have an equation. Now I've got r. I still don't know what the initial value is. Okay? And so now I go back and I go, well, what else do I know? And what am I trying to figure out? Well, I don't really know anything else. I've used this information. Okay? So I'm sort of down here. I'm trying to figure out the time when n is 10% of the initial value. Hold on. Now that we've talked about the half-life being 50% of the initial value, we could also write 10% of the initial value in the same way, can't we? Okay, so we're trying to figure out the time when the amount, we want that in black, when the amount of cesium is equal to 10%, and when we find 10% of something, well, it's 0.1 multiplied by the initial value, right? So we're going to substitute that in for n over here. Okay, so like I said, there's my equation now, and now I'm trying to find the value of t when the amount of cesium is 10% of the initial value. Right, and I just realized my recording limit is 15 minutes and I'm about to run out of time, so we're just going to talk through this pretty quickly. So again, we've substituted this into there, okay, and we can see again that the zeros cancel out, leaving me with this. I take log of both sides. I've just written that like that instead of writing down ln there, which gets rid of the e. So I'm left with that. I can solve for t. T equals this divided by this, which equals 73.08. So I can just write a rounded, it will take about 73 years. Or you could say it will take 73.08 years, because this is the kind of thing, unlike banking interest, it's not happening every year. It's actually happening throughout the year. So you could say 73.08 years. It's not going to be right on 73 years. Okay. Also, it's a good idea when you calculated r earlier, keep that in your calculator so you use the most accurate value of r. That's always a good idea. Okay, I got 10 seconds left, so I'm just going to stop there.